Good morning, everyone. Welcome to Bussmann University, a series of webcasts where experts from the Bussmann series team cover today's most pressing overcurrent protection topics. My name is Shannon Stokes. I'll be your moderator for today's webcast. Today's webcast focuses on selective coordination, and our speaker is Joe Pavia. Joe has nearly 30 years with Bussmann Series Solutions, currently serving as field application engineer. He specializes in training on the design and application of overcurrent protective devices and equipment in electrical distribution systems. He serves on a UL panel, active in IEEE, IAEI, and NFPA activities. Throughout this webcast, you're welcome to submit questions through the question and answer chat window, and we'll do our best to answer them while Joe is speaking before the end of this webcast. In the next day or so, you'll receive an email with a link to watch this webcast and our previous webcasts on demand. Be sure to check out our upcoming webcasts as well. I will now turn it over to Joe. Joe?
Thank you, Shannon. Good morning, everybody. Let's begin with selective coordination. And the key thing is, are we in compliance with the National Electrical Code? So what I'm going to do is, I'm going to basically define what is selective coordination. We're going to look into NEC requirements and applications themselves, and then we're going to do some examples. We're going to basically look at a breaker system, then we're going to go into a fuse system, and then finally we'll go into a fuse and circuit breaker system and look at the selective coordination for each one of them. What is selective coordination? And as you can see in the two diagrams that we have, over on the left side, this is without selective coordination. So the fault occurs at the right lighting panel or light ballast itself, and it knocks out that one panel itself, but then it goes up to that second panel. And when it goes up to that second panel that feeds all the other lighting panels, now we have a blackout. And this is in violation of the National Electrical Code, and so we need to comply with that. So this is lack of selective coordination on the left-hand side. On the right-hand side now, we have selective coordination, where the ballast or something shorted out on that panel, and we only knock out that one overcurrent protected device feeding that light fixture or whatever the load that we're basically looking at. This is selective coordination, and this complies with the National Electrical Code, especially on certain sections that we'll get into. All right, so let's start with the definition of the National Electrical Code. Now, the National Electrical Code started in 2005 with a definition for selective coordination, not coordination, but selective coordination. And then in 2014, they basically defined it even further because there was some misconceptions on what was going on. So the definition is this: the localization of an overcurrent condition to restrict outages to the circuit or equipment affected, accomplished by the selection and installation of overcurrent protection devices and their ratings or settings for the full range of available overcurrents from the overload to the maximum available fault current, and for the full range of overcurrent protected device opening times associated with those currents. So we're looking at all currents and all times. So the full range from zero currents all the way up to the available fault current, and from zero time all the way up to when the opening of the overcurrent devices open up. Okay, so that's the definition. And if you look to the right, all right, we basically throw in time current curves. We do time current curves to see if we do have coordination. But selective coordination, remember this, when we're talking all currents and all times, does the time current curve truly give us all current and all times? It can give us all currents to a certain extent, but doesn't really give us all times. It really only goes down to 0.01 seconds, which is just over a half a cycle. So what happens between 0 and a half a cycle? We don't know what that happens, so that's where we have to take a look at on the time current curves. It stops there, and so we need to look at something further sometimes. So the full time, usually 30 seconds and greater is your overload type scenarios, and fault current will happen usually at 0.01 seconds and less. So the time current curve will give us a certain amount of selective coordination, but it doesn't give us all times in this aspect. All right, so what does the National Electrical Code, and where does the National Electrical Code require selective coordination? And that's the key. So in Article 620.62 with elevators, Article 645.27 for critical operating data systems, 695 for multi-building campus style, for basically for fire pumps that we're looking at. Then we look into the emergency system type deals, which is Article 700.32, talks about emergency systems. And then you got legally required standby systems, which is Article 701. And then finally, we come into 708. As you can see, I have not talked about Article 517, which is hospitals. They don't require selective coordination. They just require coordination. We are only going to talk about selective coordination in this time. All right, so let's look at elevators. And so the key thing here in elevators, we're looking at Article 620.62, and it talks about selective coordination. And here's the kicker. Where more than one driving machine disconnect means it's supplied by a single feeder. So if you just have one elevator, we don't need selective coordination. They're not really talking about selective coordination. When you have two elevators, that's when we're talking about that needs to be selectively coordinated. And those two elevators, wherever that one feed, so in this case here, elevator 1 and elevator 2 are fed from B1 feeder. All right, and in this case here, both of the elevators need to be selectively coordinated with B1. Now, does B1 need to be selectively coordinated with A1? And the answer is no, because the elevators themselves are fed from the feeder, that one feeder. All right, so wherever that one feeder comes into play, if you have elevators on each side of the building fed from the switch gear, what is that one feeder? Well, the one feeder could be the main. And so it needs to be selectively coordinated all the way up to the main. In this case, we have that one feeder, which is B1, and it only needs to be selectively coordinated up to that one feeder, which in this case is B1. All right, now we've done with elevators for right now. Let's look into selective coordination for emergency systems. Right, and so emergency systems, the definition in Article 700.32, it states emergency systems, overcurrent devices shall be selectively coordinated with all supply side overcurrent protected devices. So that means all. So that means that C, down on the right-hand side, C, D, and E must selectively coordinate with B1 and A1, as well as B2 and A2 on the emergency side with the generator. So C, D, and E needs to coordinate with all supply side overcurrent protected devices. And this basically applies to Article 645, which is the fire pumps, 701, as well as 708. All right, so here's the other added in the National Electrical Code, little added wording, and it says selective coordination shall be selected by a licensed professional engineer or other qualified persons engaged primarily in the design, installation, or maintenance of electrical systems. The selection shall be documented and made available to those authorities having jurisdiction, basically, so authorized to design, install, inspect, maintain, so on. All right, so the electrical inspector may basically require to show them that it is selectively coordinated. And so they need to show documentation for that. All right, so on the right-hand side, we have, your time current curve, which is in the middle. And we always use that. But then on the bottom and as well on the top charts basically are chart that we need to look at to see if breakers coordinate and see if fuses coordinate correctly. All right, so let's look at really quick and summarize the National Electrical Code. Elevators. So elevators need to be selectively coordinated when we're using 2 or more elevators. Critical operating data systems, multi-building campus styles, basically your fire pumps, emergency systems, legally required standby systems, and critical operating systems all have to be selectively coordinated and are required based on the National Electrical Code. Now we move down to Article 517, which is essential electrical systems for hospitals. And as you can see, it says coordination, not selective coordination, just coordination, which usually talks about 0.1 seconds. So 0.1 seconds and above, I must be coordinated. Well, that's easy to see on the time current curve. All right, so that is Article basically 517 under hospital requirements. And then finally, we have the non-critical systems, which non-critical systems, it's good to be selectively coordinated, but the National Electrical Code does not say that you have to be selectively coordinated. All right, so let's get into some examples. All right, so selectively coordinated, we're going to take a circuit breaker system and have a look at what do we really need to do in a circuit breaker system to make sure that we comply with the code and make it selectively coordinated. All right, so here's what we have to do first. Number one, we definitely have to do a short circuit study. We have to calculate what is the available fault current at the point of that load or at that panel that we're doing selective coordination for. That's number one. We have to do a short circuit study. Number two, now we have to do a coordination study. And so if you use the SKM program, ETAP program, or ePower, right, you're going to do the short circuit study and then go about doing a coordination study. Now, this is not a selective coordination study. It's a coordination study. Big difference. And so over to the right, you're going to see the time current curve. And that's what we look for to see if everything coordinates, not selectively coordinates, but coordinates in general. And so this gives us coordination, not necessarily selective coordination. Now, it depends on where our fault current lies based on the short circuit study. And then we'll kind of move into what we're going to be looking at. So in this case here, most of your time current curves, if not all, stop at 0.01 seconds, all right, which is basically a little bit over a half a cycle. What happens if the fault current's great and it's showing below 0.01 seconds? Then we have to look at the tables, the breaker tables, breaker tables to see if they selectively coordinate. All right, so let's look a little bit into breaker settings. And we look at breaker settings now. So we've got some of the bigger breakers, such as the large insulated case circuit breakers, as well as the low voltage power circuit breakers. You know, they have the different settings. All right, so the different settings is, you know, you got long time pickup, short time pickup, long time delay, short time delay, and then you've got your instantaneous. Well, if you look at the long time delay, long time pickup, as well as short time pickup, short time delay, that is all overload. All right, and that is basically 0.1 seconds and above. If we want selective coordination, we're looking at all times, all currents, which is basically below the 0.01 seconds. And I'm going to give you guys an example of what selective coordination is and what is coordination. And you guys can start seeing what's the difference between it. So coordination is basically just looking at time current curves. Selective coordination is looking at everything. And so the key thing here is your instantaneous trip. As a rule of thumb, we could say the instantaneous trip's always set at 10 times as just a rule of thumb. So if I have an 800 amp breaker, that instantaneous trip 10 times is going to be 8,000 amps. So that means anything, if the fault current exceeds 8,000 amps, I could possibly lose that 800 amp breaker. Wherever it is in the system, it's possible that it can open up if it's feeding that fault downstream, even with a 20 amp breaker possibly. So we've got to see if those two truly selectively coordinate. All right, so let's look at some time current curve. So here we have a time current curve. And whoops, I'm sorry, I apologize. I hit the wrong button again. All right, so we've got a time current curve here. And this looks like all of these coordinate. They do coordinate, but we have this issue down here at the bottom, right? that we got some overlapping. But again, remember, we are talking above the half cycle mark. That's not all times. This could be all currents, but it's definitely not all times yet. And so we've got to look at what happens below 0.01 seconds. So to get a better understanding of what's going on, let's do an example. So here's my first question for you guys. Here's our time current curve. And the question is, are these two circuit breakers selectively coordinated? Right, so we've got a 150 amp breaker and a 20 amp breaker. Are they truly selectively coordinated, or are they coordinated? Well, in my opinion, they are coordinated. But what do we need? We need to look at what is the available fault current. So let's look at the definition again. All right, so the definition is this: for the full range of available overcurrents from overload to the maximum available fault current, and for the full range of overcurrent protected device opening times. All right, so from 0 all the way up to when it opens based on the fault current or overload. All right, so we did a fault study. And let's say the fault study is calculated at 500 amps. That's the maximum available fault current I'm going to get is 500 amps. We can see on the time current curve that the red circuit breaker will open on a 500 amp fault, and the blue breaker will take 43 seconds to open up, right? And it'll start unlatching a little bit before that, but we know that the red breaker will totally clear the fault before the blue breaker starts to open. In this case here, we can see that it is selectively coordinated based on the available fault current of 500 amps. Now, what happens? That's a 500 amp fault. What happens when we get a 1,000 amp fault? Now, are they selectively coordinated? Well, it's tough to tell on the time current curve. So when I did my fault calculation, I calculated 1,000 amps for the available fault current. Now we know that the red breaker is going to open up, but will the blue breaker open up as well? So the blue breaker in this case here down below, it can start unlatching, but it may not totally clear the fault until, almost 8 seconds, 7 seconds, something like that. But once the breaker starts to open, it's going to open. It's just a matter of time. So can we tell that the two breakers are selectively coordinated with the time current curve? And the answer is no, because the 1,000 amp is right in the middle of the blue breaker. So the blue breaker could possibly open up, or it may not. What do we look at? Now, we have to look at the manufacturer's time current curves. We can do that, or the charts. So let's look at a quick time current curve. All right, so here was the BAB. All right, so let me go back real quick. So we have an FD breaker, just a 150 amp breaker, and then we have the BAB 20 amp breaker. So I'm going to show you a quick curve on the BAB breaker. As you can see, over to the left side, we see the time, 0.01 seconds. That's where all time current curves usually stop in any of the computer programs. They don't go below 0.01 seconds. But as you can see, that hockey stick type scenario that breakers have, that boot or foot we're looking at, is really at 0.08 seconds, which is your half cycle, right? And it's going to open up at that point. Now, if you remember, our fault current is 1,000 amps. So if we look at 1,000 amps on this time current curve, it's going to be right here. And our blue breakers came right into play on that design. And so because the red breaker and blue breaker, so the FD breaker and the BAB breaker, both of them could possibly open up, so based on the time current curve. So now we've got to look at the manufacturer's chart, circuit breaker chart for selective coordination. Every breaker manufacturer has these charts, all right? And so this tells us that up at the top, we have the line side breaker. What was our line side breaker? It was an FD breaker, 150 amp. So here's our F frame. It was just a standard thermomagnetic breaker, 150 amp, 200 amp frame with a 150 amp trip setting, right? And so that's what we had on our line side. Our load side was the 20 amp, over at the left, 20 amp BAB breaker. And as you can see the line, we had the BAB breakers right here, up at the top gray type area, but that's the load side breaker. So load side breakers on the left side, line side breakers on the top. And if we come across, we've got the 20 amp. All right, so we got the 20 amp breaker. We stop at the F frame, and we show that these two breakers, the 20 amp breaker and the 150 amp breaker, will selectively coordinate up to 1,500 amps or 1.5 K amps. All right, so we're talking 1,500 amps. They'll selectively coordinate. And so what was our fault current? Our fault current was 1,000 amps. And so we are selectively coordinated with a 150 amp on the line side and a 20 amp BAB breaker on the load side. We are selectively coordinated. And as you can see the charts, we can increase that or decrease that based on this chart itself. All right, so in this case here, we know if you look at the right, the 1,000 amp is going to be selectively coordinated based on the charts, even though the time current curve shows it hitting the blue breaker. Now, so at 1,500 amps is the key. We are selectively coordinated at 1,500 amps. What is going to happen at a 2,000 amp fault current? So we did calculations, and now we have a 2,000 amp fault current. Based on the charts, though, we have to look at the charts, and we found out based on what we looked at on the charts that it is not selectively coordinated. So this 150 amp FD breaker and the BAB 20 amp breaker on the right will not be selectively coordinated because the blue breaker and the red breaker will open up. And so what do we have to do to modify that to make sure that we comply with the code and get selectively coordinated? And so we would have to relook at the chart, okay? And so we got a 2,000 amp. So we still have our 20 amp breaker, right? And so now we come across and we come into 2,200 amp, all right, which covers it. But now we have to go to a 225 amp circuit breaker. So if we go to a 225 from 150, guess what? We got to jump up our cable size to feed that 20 amp panel or 20 amp breaker panel that we're going to be using. So we have to jump to a 225 amp breaker, FD breaker, instead of using the 150 amp FD breaker. We want to make sure that we catch this before we start installing the conductors and everything, because this may be an issue. The time current curves, all right, showed us that it's coordinated, but not necessarily selective coordinated. And the code requires selective coordination all times, all currents. All right, so here's the time current curve again that we're showing. 150 amp breaker on top, 20 amp breaker below. The correct answer is maybe. Why? Because we need to know the available fault current at that time. And once we know the available fault current, then we can make a decision, is this selectively coordinated or not? All right, so we would have to use the time current curves and the manufacturer's charts. All right, so that's the breaker system. So that's a breaker system that we were looking at. Let's look at a all fuse system. What do we have to look at in an all fuse scenario? All right, so again, we have the time current curves. And remember, the time current curves go to 0.01 seconds again. So in this case here, we have a 300 amp Class J fuse, the LPJ, Bussmann LPJ fuses, a 300 amp, and then we have a 600 amp LPJ, 600 amp fuse. And as you can see, the fuses look like they're selectively coordinated, right? But they're definitely coordinated. What's happening down here, though, below the 0.01 seconds? That's what we need to look at based on the fault current, or is it really based on the fault current? Let's see what we have to look at. Okay, so in general, for fuses, if you're in the same family of fuse, so for instance, if you have a Bussmann low peak fuses, so either the Class J's, okay, so we've got two Class J's here in this case, or the RK1s, which are the low peak fuses, the LPSs or LPNs. If we have two of the LPSs together, right, it's automatically a 2-to-1 ratio. So I no longer have to do the available fault current. All I have to do is make sure that my ratio is at least 2-to-1. So for instance, give me an example. If I have a 30 amp fuse, if let's say the red fuse is a 30 amp fuse and the blue fuse is a 60 amp fuse, well, 2 times 30 is 60. I have a 2-to-1 ratio right there. They will be selectively coordinated across the board for all currents, all times. What happens if I have a 60 amp fuse? Then I have to use 120 amp. Well, we don't make a 120 amp fuse. We make a 125 amp fuse. So I would use a 125 amp fuse. And again, they would be selectively coordinated for all times, all currents. Now, in this case here, we have the 300 and a 600 amp. So 3 times 2 is 600. They're going to be selectively coordinated for all times, all currents. So no need to basically plot the curves if they're in the same family, and no need to do fault calculations for a fuse combination rating. Right, so here's what we're looking at. I basically corrected my slides except for on this one. But so again, we have a 600 amp LPJ on the line side. So here's my load side. My load side's on this side. My line side is down here. So we have an LPJ, which is right in the middle in the dark gray area, right before we moved into the white, right? And it's, was it 1, 2, 3, 4, 5, 6, 7, 8 lines up. All right, so we've got the LPJ fuses. And if we go all the way across to the LPJ on the load side, which is on the top side, LPJ, we show it's a 2-to-1 ratio. And so across the board, as long as I maintain a 2-to-1 ratio across the board, it'll cover for all times, all currents, and the fuses will be selectively coordinated. And all fuse manufacturers have these charts for their fuses. And as long as I stay in the same family of fuses, we're talking about a 2-to-1 ratio. So let's take a look at this. All right, so we've got a one-line diagram on the right-hand side. And so am I selectively coordinated for these fuses on this type of system? So this is an emergency system. So we have our generator for the emergency side, and we have the normal system. And so remember what I said before, C, D, and E must selectively coordinate with all upstream devices. All right, so as we go through it, so C, D, and E must coordinate with B1 and A1. And C, D, and E also must coordinate with B2 and A2 and be selectively coordinated. All right, so do I have a 2-to-1 ratio? Well, I'm using a 20 amp fuse. All right, so the low peak 20 amp fuse, which is a cube fuse. If we go to B1, that's a 200 amp fuse. And in this case here, I have a 10-to-1 ratio. It'll selectively coordinate. Now, and then I have A1, which is a 20 amp fuse up to a 600 amp fuse. That's a, a 300 or 30-to-1 ratio. That would definitely selectively coordinate. And then if I look at B1 to A1, Again, I just need a 2-to-1 ratio, so I know B1 will coordinate with A1. And then if we move over to the generator side, basically we're looking at the exact same thing. We did not have to plot the curves. We did not have to calculate the available fault current. We know that this system is selectively coordinated, and it's good for at least 200,000 amps because the fuses are at least 200,000. These fuses in this case are at least 300,000 amps. So available fault currents we don't have to worry about as well. All right, so we have basically localized that fault current at that 1 for L3 that went out, and then we isolated that so L1 and L2 lighting was not affected because E or L3 basically was taken out with the fuse on E. All right, so let's get into reality. Okay, let's look at a fuse breaker scenario. So we already looked at a breaker scenario, and then we looked at a fuse scenario. Now let's look at a fuse circuit breaker coordination system. All right, so as you can see, we plotted our curve. So we basically, for a fuse breaker scenario, we definitely have to plot our curves. And then we also have to do the available fault current or calculate that available fault current to find out where it falls into play. All right, so as you can see, we basically put the one-line diagram up there and then drew the time current curves. We have a 20 amp fuse at the branch level. Then we have a 150 amp fuse, let's say at the feeder level, and then a 600 amp fuse. So the green is the 600, the blue is the 150 amp, and then the red is your 20 amp fuse, right? So we have to calculate the available fault current, and then we have to plot the curves, because we want to make sure that we definitely have selective coordination above the 0.01 seconds that our time current curve gives us. But what about higher fault currents where the time current curves really don't show us? Then again, we have to use the charts. So let's take a look at the chart. Again, over to the left, we have the 600 amp breaker, 150 amp breaker, and the 20 amp fuse, right? And given that, we have the 20 amp fuse, we have a 150 amp breaker, which is just an FT thermomagnetic breaker. It tells us, the chart tells us it's good up to 35,000 amps. Well, the 35,000 amps is the breaker interrupting rating. The fuse has a 200,000 amp interrupting rating. The breaker, though, is limited to 35,000 amps. And so as we can see in the chart, the breaker and the fuse selective coordination is up to the breaker interrupting rating. And in this case here, it's 35,000 amps. And if you take a look at this chart itself, in general, you're looking at basically a 2-to-1 ratio. All right, so if a fuse is on the load side, and then you have the breaker on the line side, it's almost like a 2-to-1 ratio. In this chart, it is basically. So we look at a 50 amp fuse here, over to the left, we come across and we stop at a GHB, which is the very first column. It calls out 14. Well, the GHB, the maximum, is a 100 amp breaker. Well, what's the ratio? 2-to-1, right? Again, we can go to a 60 amp fuse and then use the EGB breaker, which is, what's the rating? 125 amp rating. All right, and we can go up to 18,000 amps. These are the maximum ratings for these breakers. That's their interrupting rating. And that's why the maximum is their interrupting rating. And so we're showing basically a 2-to-1 ratio for a lot of these when you have a fuse on the load side and a breaker on the line side, right? So let's see how easy this is to do. All right, so Bussmann has the QSCP panel, we call it. And it's a fusible load center, basically. And as you can see in the picture, in the middle, you can have a fusible main, a main switch, or main lug only, just like you can with your standard load side breaker panels and so on, right? You can have 15 20, 30, 40, all the way up to 100 amp branch circuits, all right, with the main being a 200 amp, a 400 amp, and even a 600 amp now. And then down below at the very bottom of this panel is your spare fuses, right? And so if you're thinking about it, we're at a lighting panel. When does the fuse ever really go in a lighting panel itself? It's when the ballast shorts out or something happens on the wire, so on. Are we changing the fuses out all the time? The answer is no, right? But we do have spare fuses. And if the customer, if you're a design engineer, you design this in, the customer can see that, hey, we can have spare fuses. And if a fuse does open up, he's got spare fuses there to basically change out the ballast and then put a new fuse in there, right? We have single pole, 2-pole, or 3-pole devices as branch circuits. So you can have a 3-phase system or a single-phase system. The panel, and here's the key, is 20 inches wide. So it's the same size as basically a breaker lighting panel. And then we have how many branches? Well, you can have how many circuits? So basically you have 18 circuits, 30 circuits, or 42 circuits. Right? And we do have rejection features because since it's a panel board, it has to have rejection features. So we have, if you're going to put all 15 amp circuits in there, all the switches have to be 15 amp switches. If you're going to put a 20 amp fuse in there, all the switches need to be 20 amps, right? And so the 20 amp can handle the 15 and 20 amp. So if you're going to use 10 gauge wire, then we can use a 30 amp switch, and then it can fit the 15 and 20 amps as well. You can't go higher. And then the switch will look like this. So it's bolted onto the bus bar. All right, here's the fuse. It's finger safe, touch safe. We basically have a light indicating. So when the fuse does open up, if you see right below the handle, there's a little dot to the right. That is when if the light lights up, that means the fuse is opened and you need to change the fuse out. But OSHA requires us to make sure that we check to find out why the fuse opened, and then we'll replace the fuse. Just like when a breaker opens up, to reset it, we have to find out why it opened up, and then we can reset it. Right? Everything is IP20 finger safe, and then again, the branch circuits can go up to 100 amps at this time, and we have time delay fuses and fast acting fuses up to 600 volts. And then the panels are going to be rated 200,000 amps as well as the switch. We do have lockout tagout. So you have a lockout tagout. If you look at the upper switch, there's going to be a little notch there and a ring that you could basically lock it out or tag it out. And then finally, to make it a little bit easier as well, we have for elevators, we have the power module. All right, so for elevators, we still need selective coordination. And so this is a fusible switch with a shunt trip in there, because it ties into the fire system. And some of them are required to tie into the fire system with the smoke detectors and also with the sprinkler systems as well. And when a fire occurs in the shaft, if it's sprinkled, it requires shunt tripping that elevator to go down to a floor that's not on fire, and then lock in the brakes, and then you shunt trip the switch itself. A better picture of that would be, here's the inside enclosures. You have your control transformer in there. You've got your Class J Bussmann fuses for selective coordination. And again, a 2-to-1 ratio with upstream fuses. And then you have a shunt trip system type deal to tie into your fire system. The enclosures can be NEMA 1, 3R, 12, or 4, or different options that you have. All right, so let's want to bring up that surge protection is required on emergency systems as well as elevator systems. If the elevator, so let's talk about elevators. If the elevator is on emergency system, then you are required under 620.51 to put a surge protection in that panel. All right, and basically what it says is where any of the disconnecting means in 620.51 has been designated as supplying an emergency system load, surge protection shall be provided. So that's on your elevator system, if it's considered an emergency on the emergency system. Over on the right-hand side, we look at Article 700. And 700 is your emergency systems. And it basically states, a listed SPD, which is a surge protection device, shall be installed in or on all emergency systems, switchboards, and panel boards. And in the picture down at the bottom right, we're seeing that this is a surge protector on the far right, and it's basically on the load side of the bus that it's wired into and then goes to ground. In the middle is one of our external surge protectors, and they basically are mounted externally to the panel itself. This way you can see the light on, and then if you have, when it does, the MOVs sooner or later will go, and then you would have to change them out, and you can see that. The one on the far right does have lights as well, and it'll turn red when they no longer are good, and then you just pop out the middle section and put it in. You don't have to unwire any of the stuff on the right. The one in the middle, the external one, you would have to unwire. All right, so let's look at an example, a real life example. All right, I basically took out some of the names and stuff like that. This way we could take a look at what really happened. So what is the first thing we have to do? So we have a one-line diagram that is given to us. We have the utility is supplying a 1,000 kVA transformer. The transformer is a 4160 to 480 volt transformer with 5.75% impedance. What are the first thing we're supposed to do is do a fault calculation. So we basically take the fault calculation, and at bus AB, I want to call it bus AB, which is your switchboard, we have about 22,000 amps available, so 21,830, right? And then at the power panel, let's just call that C, at the power panel, which is a main lug only type power panel, we basically have almost 13,000 amps. So we have 12,572 amps. And then finally, at the load center, which is D, we have about a little bit over 4,000 amps. So 4,159 amps that we have. So we've done our fault calculation. Now, the next thing we do is we do a a coordination study, all right, where we basically throw time current curves together, right? So we have, let's just go over this real quick. A is a 1,200 amp breaker. B is a 400 amp breaker. C is a 115 amp breaker. And then D is your 20 amp breaker. I didn't put that down there, but it is. Our conductors, remember, look at our conductors today. Today, our conductors are 500 MCM, all right, feeding lighting panel or panel C. And then we have number 2 conductor feeding panel D, right? So we have 500 kc mil feeding C, and then a number 2 feeding D. So let's take a look at the time current curves, okay? To make sure that we have selective coordination, up at the right-hand side, we have the circuit breaker charts. I know it's the little eye chart, it's tough to read a little bit, so if you can blow it up a little bit, it's possible, or get closer to your computer. So we're showing that the LHH breaker and the GHB breaker, on the load side, GHB, and on the line side, the LHH, it can handle 7,600 amps and still be selectively coordinated. So on the time current curve, that's the purple breaker. All right, so we got the purple curve, which is the 20 amp breaker. And then we've got, it's kind of like a brown type breaker. And that is the 100 or 200 amp frame, 175 amp breaker. All right, and we can see that those two are selectively coordinated based on the chart, and they're coordinated based on the time current curve. So they meet the standard for the National Electrical Code. But what happened? Remember, C was at 115 when we first designed it. Well, we couldn't use a 115 amp breaker, right? So let me go back a little bit to show you. Remember, so we used a 115 amp breaker to feed this, or a 100 amp breaker. I see a lot of 100 amp breakers feeding this main lug only panel. And in this case here, we can't do that. And what conductors would we use? A number 2 or a number 3 if it was a 100 amp breaker. Well, to be selectively coordinated, now C is going to have to be a 200 amp frame with a 175 amp trip setting. Well, that 175 amp trip setting now, we have to now change our conductors from a number 2 to now using 2-aught conductors. And now D is selectively coordinated with C. But as you can see, is C really coordinated with B? And B is your red curve. And you can see that it's not selectively coordinated. All right, and it's not really even coordinated because they're overlapping. So if you lose C, most likely you're going to lose B as well. And B, we use an 800 amp frame breaker with a 400 amp trip. And then at the top, the A breaker, we used a 200 amp frame breaker with a 1200 amp trip. And so we're trying to selectively coordinate, and the only selective coordination that we have is with D and C. And so we had to use bigger frame breakers to try to get close to this selective coordination, which we didn't accomplish yet. Right? Let's look at what else we can do. All right, and so in this case here, all we did was use the QSCP panel, main lug only, and used fuses. And over to the right is our time current curve. So the purple line is your 20 amp fuse curve. The brown curve is your 100 amp now. So that number 2 conductor that we first installed is now okay to use, because now we can use a GHB 100 amp breaker, and we're still selectively coordinated with that fuse downstream. That also gives us now, we get to change circuit breaker B, which is the red curve line. And if we go all the way to our one-line diagram, now we get to use the LHH 400 amp. Instead of using an 800 amp trip with a an 800 amp frame with a 400 amp trip, now we can use a lesser expensive breaker, which is the LHH breaker, in play for the B, for breaker B. And then A, we're still trying to coordinate the 400 amp breaker with A, which is the 1200 amp. And in this case here, we have to use a 2000 amp frame. We still don't have selective coordination. We have coordination, but not selective coordination, because as you can see at the bottom right on the time current curve, that they overlap, which will create both of them to open up if a fault is greater than that line itself. Can we improve this? And the answer is yes. But let's first take a look at the chart. So I did bring the chart up, so we're going to take the chart for the 20 amp breaker, 20 amp fuse, the cube fuse with the Q in the QSCP panel, and the 100 amp GHD breaker. So the chart is this. And as you can see, the 20 amp fuse, we go over to the GHD breaker, all right, 100 amp, and we're coordinated all the way up to 14,000 amps. 14,000 amps is the interrupting rating of that breaker, the GHB breaker. So that's the max anyways that we can have a fault current because of the breaker scenario, right? So the 20 amp fuse will selectively coordinate with the GHB breaker, 100 amp GHB breaker, up to 14,000 amps. And so how much fault current did we have? We had 4,000 amps, a little bit over 4,000 amps, so we're good to go. And then finally, if we add a second line, so if we put a 100 amp main in our QSCP, all right, or use the Eaton Power R CFQS panel, we have a 100 amp, which you look at the time current curve, the purple line is the 20 amp breaker. The orange line is the 100 amp breaker. And remember, 2-to-1 ratio, that's all we need. So a 20 amp 2-to-1 ratio would be a 40. We have 100 amp instead. We're good to go. And then now, look what we can do to the breaker in the red. We can get a less expensive breaker again. We can go from an LHH breaker back to a KD 400 amp breaker, which is less expensive, all right? And now we selectively coordinate. The 100 amp fuse will coordinate with a 400 amp breaker. And then guess what we did to breaker A? We went from an ND, I believe, to an RG. Now we go to a 1200 amp frame with a 1200 amp trip setting instead of going to a 2000 amp frame with a 1200 amp trip setting. So now, because we put fuses on the load side for the emergency circuits, the QSCP panel on the load side with either a main fuse or we can have it fed from a main fuse. Now we can use less expensive breakers upstream as long as they meet the fault current ratings or the interrupting ratings that they need for that. And in this case here, the KD 400 and the electronic trip 1200 amp breaker A coordinates up to 35,000 amps, and that's what the charts will show us. Even though it doesn't look like they coordinate down here at the bottom right of the slide, but they do. And that's how we would look at time current curves, right? So we look at time current curves and the charts. So in summary, all right, the first thing we have to look at is in the design phase, we need to really calculate the available fault current. Can we get exactly accurate? Well, we can get close. So we should know approximately what our available fault current is. And then we have to choose the correct design for selective coordination. Remember, all times on the design, all currents. All times do not say 0.01 seconds or 0.1 seconds. It's 0 all the way up. Because if we're at 0.1 seconds, that's still over a half a cycle. And the National Electrical Code says all times, all currents. And then beyond the approval phase, you know, contractors will look into it and stuff like that, and then they may switch manufacturers on the different breakers or fuses or so on. We need to take a look at, are we still selectively coordinated in the approval phase? And then finally in the construction phase, when it's installed, right, we want to make sure that the conductors are sized properly for the overcurrent protective devices and make sure that the overcurrent protective devices are selectively coordinated with each other. All right, so quick summary. When we have an all circuit breaker scenario, so we have circuit breakers, lighting panels, all the way up to the main. Two things we have to look at then. We have to do the fault calculation. We definitely have to do that. Then we have to do the coordination, which is the time current curves. And then finally, we have to look at the charts based on the available fault current at the line terminals of the panel. Right? Now we look at a fuse scenario. Do we have to do a fault study? The answer is no. All right, but a lot of times we always do it just to check, make sure our panels are done, but we don't have to do it to check for selective coordination on fuses. All we look at is a 2-to-1 ratio. So if I have a 20 amp branch circuit, I can use a 40 amp main and they'd be selectively coordinated all times, all current. A lot of times what I see is 20 amp breakers, branch breakers, or 20 amp fuses with 100 amp fuses in the main. Okay, we could still use main lug onlys if we wanted to, but a lot of times I see a 100 amp main with 20 amp branch fuses, and we know that that is selectively coordinated because that's over a 2-to-1 ratio, and it's usually the same family type fuses. And then finally, a circuit breaker with fuses. Remember, fuses always have to be on the load side of that circuit breaker, and a lot of times it could be a 2-to-1 ratio. And on our last example, we showed that if we put a 20 amp fuse feeding from a 100 amp fuse, all right, and then upstream from that, all right, so upstream from that, we can basically use less expensive breakers as long as they match and look at the selective coordination as well as the interrupting rating and fault current. And then finally, using the QSCP resolves a lot of the selective coordination issues because I can put a fusible main, 100 amp, and use fused branches, 20 amps, 15 amps, 30 amps, and so on, and I get my selective coordination with no issue at all. And then finally, Bussmann has several resources. So you've got the industrial application for circuit breaker coordination charts. You can basically Google Eaton. You could type in IA012000002E, and there it gives you the breaker charts that you would possibly need for an Eaton breaker system. We also have the application notes 3148, which gives you the fuse selection ratio chart, as well as the circuit breaker fuse coordination tables that you may need. And then finally, QSCP specifications. If you guys need it, you can always get in touch with Bussmann or shoot me an email. I'll be glad to send it out to you guys. And then we have a fault calculator, FC2, that helps you calculate the fault if you're in the field. So in general, Quick Specs solves a lot of your selective coordination issues as well as meeting the code. And so I'm concluding this. I had to cut myself off quick, but we got through this all. If you need any questions, please, here's my contact information. It's Joe M. Pavia at Eaton.com, and my telephone number is 317-665-1956, and I'll be glad to assist in any way for selective coordination. I'm going to turn the presentation over to Shannon for right now, and she will close it out. Thanks, everybody, for your participation.
Thank you so much, Joe. Thank you for walking us through selective coordination. Just a reminder that Bussmann University allows you access to all of these webcasts. The first one are already available on demand. This one will be made on demand tomorrow. And if you'd like to register for the future ones, you can do that within Bussmann University. This concludes today's webcast. On behalf of the Bussmann Series team, thank you so much for your time. Have a wonderful rest of your day.